Welcome to everyone for our today webinar, Reservoir Solution Impact on Reservoir Production Performance. I am Abdullah Abdurrahman, Business Development in Reservoir Solutions. I would like to welcome you all to this session, inshallah. We will do just 5 minutes presentation about Reservoir Solutions and also to introduce our instructor for today's session. So, Reservoir Solutions is a company specialized in providing technical studies and courses for oil and gas professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services include technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researchers like PhD and master degrees, assisting in writing technical support for academic researchers like PhD and master degrees. Also, we are assisting in writing technical papers and publishing. We're also providing technical petroleum courses by industry expertise, and we are providing mentorship programs. For the upcoming events for Reservoir Solutions, we have 2 courses. We have one course for 3D modeling for natural fracture reservoir modeling that will start today, inshallah. Also, we will have another course that will be into the next month about the practical seismic interpretation. For the details for these courses, we will send the details for the course content into the chat box. For our today webinar, our instructor is Mr. Magal. Mr. Magal is an experienced stratigraphic reservoir geologist and consultant with expertise in high-resolution sequence stratigraphy, supported by sedimentology and reservoir geology. He has 38 years of experience in the oil industry and has been lecturing at Brazilian University for 26 years. He is specialized in applying high-resolution sequence stratigraphy and 3D geologic modeling to improve reservoir characterization, reservoir zonation, and hydrocarbon production. Currently, he is founder and CEO of Magal Geo Consulting, a visiting member of China-Brazil Joint Venture Geoscience Research Center, IGGCS, in China, and a research associated at the Federal University of Rio Grande do Norte in Brazil. Mr. Magal is working on high-resolution sequence stratigraphy of Jurassic Cretaceous successions from the Lusitanian and Potiguar basins and the Petrozoic successions in Sao Francisco and North China craters. Additionally, he is a reviewer for a range of well-established international journals, including Marine and Petroleum Geology, Geological Journal of South America, Earth Sciences, and Arabian Journal of Geosciences, Precambrian Research, and Brazilian Journal of Geology. So we would like to thank our instructor for today's webinar for his effort and the knowledge sharing. For the webinar rules, please ask your questions into the chat box. Please mute your microphone and camera. In case that you wanted to get a certificate for attendance, you can fill into the form that will be sent into the chat box. For upcoming events, you can join our Telegram and follow our LinkedIn page that will be sent into the Zoom chat. Also, you can contact Reservoir Solutions team by the email and the WhatsApp. So thank you all, and we hope you enjoying this session, inshallah. Mr. Magan, you can start.
Thank you, Mr. Abdullah. I'll try to share my screen.
Okay.
And then let's see. Share screen. Share. Can you see my screen right now, please?
Yes, Mr. Magan, you can start.
Okay, thank you very much for the invitation from the Reservoir Solution team, especially Mr. Abdullah. I'm very grateful for this opportunity, and I hope we succeed in having good cooperation from now on. I also like to thank everybody that has reacted to this LinkedIn post. And today we're going to talk about the impact of reservoir zonation on production performance. I must say that this is founded based on sequence stratigraphy principles. So I expect the audience has some background and some in sequence stratigraphy, because we deal about this during our talk today. Well, the first question I have to ask, starting this presentation, is, let me see here the control. What is the reservoir zone? Well, it is a subdivision into rock bodies that are mappable. When I say mappable using well logs. We're not talking anymore about seismic scale, but reservoir scale. So we map this rock body, this zone, using well logs. This rock body, this zone has properties that enable the flow of fluids within it. They are consistent and predictably different from adjacent units. And we may use geostatistics, such as flow zone indicator, to distribute properties within the zone. So this zone must be separated to each other by any kind of heterogeneity. So what heterogeneity I'm talking about? Those that control the fluid flow within a zone that is recognized within a chronostratigraphic framework. This heterogeneity may be primary, it means related to the positional process, or secondary, those associated with diagenesis. But no matter, both must coincide with sequence stratigraphic surface, so we can subdivide into chronostratigraphic zones, high resolution zones. So how can we perform reservoir zonation? Well, I give you an example, a very simple one, so everybody can follow our discussion. Suppose you have two wells, well 1 and well 2, and both wells have gamma ray black lines here. And the geologists performed a lithostratigraphic or lithological correlation, connect the yellow mossbar sandstone, the green heterolith, and the gray the shales. So just connecting rock bodies between two wells, we have this geometry of our reservoir zonation. We have 3 zones in yellow. And suppose this reservoir zonation was used to propose a project in which well 2 will inject water that may enhance production in well 1. So based on this correlation, the connectivity of the reservoir are very, very well shown. So this is a straightforward correlation, and the project was submitted, and the company approved it, and invest money to operate this injection project. What happened some time later was the water injected on well 2 did not enhance production in well one, and the big boss became very, very angry, and the geologist, a humble guy, had no answer to that failure. And then he went back to his workstation and called his colleagues, the geophysicist, the engineer, and they realized that they missed to map a fault, a subsidence fault that prevents the water from well two to reach the well one. Well, we have solved our problem, the team thought. And they called the manager again, and the big boss became even angry because this solution did not solve the project problem. So it's not so easy to understand how the project did not work. However, if you think about sedimentological and sequence stratigraphic principles, we know that we're dealing in this situation with deltaic sedimentation. Mouse bar is an architectural element of the deltaic system. And doing though, in assuming that, we see that the normal regression associated with the deltaic progradation shows clinoform, deltaic clinoform, that progressively progrades toward the depot center. And very important to note that each clinoform is separated by maximum flooding surface in green that promote the barriers, the heterogeneity that individualize each clinoform as individual zones. Pay attention that the fluid flow within the clinoform does not affect the fluid flow in the other clinoform. And based on this correlation, we can assure injecting water in well 2 never reach well 1. In doing so and showing this to the manager became happy because the company would avoid this project and save money. And maybe the team, the geologist, geophysical engineer, got promoted, right? So if you use these up-to-date principles, we may never fail in a project like that. Well, regarding the normal regression, we can zoom in one of these clinoform and see how the phases association are organized within it. And then we have the percent at time 1, time 3, and the progressive progradation of a clinoform in which proximal sediments progressively stacks on top of intermediate deposits that progressively stacks on distal strata. And then we can recognize this surface, stratigraphic surface, that delimit, that bound the whole clinoform, the maximum flood on top, the maximum flood at the bottom. And more important, we see some zigzag lines that separate some positional domains in which phases are different, proximal phase, intermediate phase, and distal phase. Since the phases or the phase association are different, we might and must expect the porosity, permeability, the petrophysical property are also different. And then the zigzag may constrain, and we have to perform our petrophysical modeling accordingly. This clinoform may be related to low stand system tract if downlaps a conformative correlation, a correlative or a high stand if downlap the maximum flood. The correlative concordance and here maximum flooding. Correlative conformity and maximum flooding. Okay. So we're talking about stratigraphic resolution that is beyond seismic resolution. Here we see a picture of a seismic line. You can see some sequence or system tract. But when you deal with high resolution, we're talking about a zooming and go to sub-seismic scale. No longer seismic, but interval correlation. And to give you an idea about that, let's show you this outcrop in Brazil, where you can see 125 meters of the sedimentary package, mostly sandstone and some shales, offshore shales. But you can also see several horizontal lines that separates, that individualize a group of strata within this 125 meter stack deposit. Zoom in, we can see that the author proposed third-order sequences, transgressive in blue, regressive in red, that are composed of Stuarine and marine and continental strata. And zooming again, change from third order to fourth order, we can see this one, the third order, can be subdivided, further subdivided into fourth order sequences. And these sequences are bounded by lower surface shales, and then we have this surface that separate our zones, high resolution zones. This is the scale where we can understand the performance, the production performance of the reservoir. So there are some criteria to identify high resolution sequences. The first one is identify transgressive and regressive cycles that must be recurrent, vertically recurrent. And these recurrence indicate trends that help us to assign high hierarchy sequences. These TR cycles and trends we can represent using Karagodin triangles in blue, the transgressive, in red, the regressive. In this case, the high sequence, high frequency, we can group into medium frequency or cluster into this one into low frequency TR sequence or TR sequences. The other criteria is mappability. Mappability is a function of a hierarchy. So hierarchy sequences has wider lateral extents than high resolution or high frequency sequences. So let's see another example from the Cenomanian and Dunvegan formation in West Canada Basin, in which you have two system tract, third order low stand system tract, and the third order transgressive system tract in green. The low stand, it can be subdivided in fourth order, that in turn can be subdivided into fifth order. The overall progression can be subdivided into fourth order cycles that show the same progression, and they can be further subdivided into fifth order sequence that also shows retrogradation stacking path. So the non-regressive is here in all scale. Again, another example from the New King Basin, the Jurassic, and have here outcrop of deltaic section, and they are prograding to the west, the direction. And this is the segmental log where you can see the distribution of architectural elements. And we use this based on core or based on outcrops to propose a conceptual model of the depositional system, in this case, a deltaic one. However, this low frequency depositional model is no longer acceptable when we are dealing with reservoir. We must go further and subdivide this low frequency model into high frequency, high resolution sequence stratigraphic model, in which we can recognize several high frequency sequence stratigraphic surface, each one separate a zone. And if you elaborate a paleogeographic map, we can see subtle changes in these architectural elements that compose our depositional system and understand the distribution phase associated with our reservoir and the heterogeneities. So the question is, which the highest resolution we must achieve? The answer is very simple. We must achieve the reservoir scale, the zone scale. It means we must be able to understand and map the heterogeneity that bound each high resolution zone. But remember, the high resolution must solve your problem and must be mappable. So when you elaborate our 3D model using sequence stratigraphy approach, we know that the main objective of high resolution is to provide an application to determine the reservoir donation and characterization, because this approach enables us to understand the spatial and temporal distribution, as well as the lateral connectivity of our reservoir that are bounded by heterogeneities. And during production, wherever the production mechanisms the oil field has undergone, data from production may be helpful to refine our sequence stratigraphic model. So new data indicates the necessity to adjust the geological model, and from the geological updated model to update the fluid flow models. So if you do this loop from geological model to 3D model, we can simulate production in the fluid flow model and observe if the simulated production match the historical production data. Be aware to not use any kind of artifact to manipulate property in fluid flow models. It's recommended to change the property in the geological model and feed again the fluid flow model and simulate production. Once the historical production has achieved and matched with the simulated production, now the models are mature enough, strong enough to forecast production. And this forecast production can be used to support production management, reservoir management, and development projects. So this loop must occur indefinitely during the life of an oil field. Now we're going to see some diagnostic situations that indicate the need for revising our reservoir donation through high-resolution sequence stratigraphy. I compiled this diagnostic situation based on my own experience and from some colleagues that work together with me. The first diagnostic situation when you have an oil field to deal with is to check if the oil field has the donation based on lithostratigraphic or lithological approach, we may have problems. Because, as you saw in the first slide, the differentiating approach, litho to chronostratigraphic, we can save money. We can see the overall evolution of the system and avoid any mistakes. So the lithostratigraphic or lithological donation does not properly represent the temporal and the spatial distribution, the lateral connectiveness, and the heterogeneity that bound our zones. That's why we have to move to chronostratigraphic, sequence stratigraphic approach. So let's see some diagnostic situation. The first one I'd like to bring you today is when you face tilt oil-water contact in an oil field. In this case, the oil produces heavy oil, so people need to inject steam to stimulate production. And these wells are only 93 meters apart, but the group mapped the tilted contact that had a difference of 10 meters between these wells. So by refining the reservoir donation, they understood that, in fact, they have two zones with two distinct oil-water contact instead of one tilted oil-water contact. The other very common situation is when you see the petrophysical modeling in one reservoir zone that shows that had this appearance. The random distribution of petrophysical properties using just statistics or whatever, but you cannot see paths, you cannot see how a fluid can flow from one well to another one well. So it's very complicated to understand how the path the fluid will take in this simulation. Rather, in this case, you had cores that indicate presence of paleosoils on top of fluvial plain, and the group modeled this accordingly. They subdivided this zone into 1, 2, 3, 4, 5 different zones, in which the yellow represents the fluvial channel belts that's developed by the find from the fluvial plain. And then, with this representation, the group was able to distribute the properties, the petrophysical properties in the yellow reservoirs, the fluvial channel belts, and then got much better control on fluid injection and fluid production in each zone. Another very, very common situation is unexpected water production. It's very, very complicated to understand this, but if you use some principles, you can see we can have some solution. This case comes from the Brazilian Cretaceous shallow marine carbonated platform in Campos Basin, in which the reservoir structurally have an antiform and the oil-water contact, and the production well, number 3, was in this position, and the group supposed that the oil-water contact will move up slowly, pushing the oil to the producer. To enhance this mechanism, they proposed inject water on top of the structure, so the water would help pushing the oil to the production, number 3 or number P. Some years later, they realized that the water, instead of moving horizontally to the top of the structure, moves through permeable zones, both in this production well number 3 and both in this injector, the zone that was submitted to injection in this injector well. So the production wells were flooded by water, and so the manager asked, what can we do? We will abandon this oil field. Well, the groups realized that science could show some heterogeneity in this view, and they decided to refine this zone into high resolution zone. And the water saturated zone was squeezed, and they never opened zone before, on top or below the water saturated zone, and production was reestablished. There are many other situations that indicate the needs for revising our evaluation, such as geomechanical problems. When you have a geomechanical problem, means we overpressure a zone because we don't know exactly the volume the zone would accept for injection. If you drill well based on seismic anomaly, we must be aware that the seismic anomaly must be constrained by the positional and stratigraphic model. Remember that low density or low velocity shales may show a seismic anomaly that may be misinterpreted as, for instance, reservoir in deep water. If you drill well in our oil field and the well cross unpredicted zones or test unexpected fluids, it means we have no idea about the spatial distribution of the zones, nor the fluids they contain. And this one is very, very important, because if you propose a production forecast without taking care of the matching with the simulated production with the historical data, we may have an economical problem. The return, the outcome of the project may be not that expected. And remember, we're here to make the big boss happy, right? So these diagnoses are very, very common, and I guess if you have ever faced some of them during your professional life. Now I show you a case study. In this case study, we will see some of these diagnostic situation and how the group overcome this problem. This is a case study on onshore Brazilian oil field that is comprises classic and carbonate and mixed the vertical section. The reservoir belongs to this unit, that is part of the first order Brazilian Pacific margin that was subdivided into 2 second orders, and the lower second order was subdivided into 3 third order, and reservoir belonged to this upper third order sequence. The oil field has an area of 10 square kilometers, and the volume of oil in place around 63 million barrels. Not so big, eh? But anyway, in 2005, the field had a 200-meter interval space. Based on well logs, we can recognize that reservoirs are highly vertically layered, okay? And we also know they are laterally disconnected. This is the gamma ray, the Hertz-Stivet, and the porosity logs. And this is the production curve of the oil field. And you can see open well flash production and very quick decline. Open well, very flash production, oil to the surface, and very quick decline, and so on. So this behavior shows us the reservoirs are very, very compartmented, are not connected. And then the oil field was approaching its economical cutoff by the end of 2005. And the group was asked, what will you do? What can we do to restore the production? And the question, among many questions, among many answers, the answer to this very important question is go back to the rocks. Why? Because the rocks provide us the primordial, the primary, the most important information about the depositional system, about the stacking pattern, about sequence stratigraphic surface, about the zones we can map in our oil field. And then go back to the rocks. The group did it and recognized the reservoir consists of coastal to shallow marine classic phases that was interbedded with the shallow marine carbonate phases. And they proposed a model in which a regressive fan, coastal to shallow marine fan, was fed to the depth center, and then they promote the salt displacement subsurface and creating gross faults. Gross faults indicate increase in accommodation, so the flooding, marine flooding took place and covered the classic sediments and the development of a carbonate platform. At the end of transgression, the maximum flooding surface was formed, and then it was exposed and have subarachnoid formed. And again, a new cycle of regressive sediments, yellow, the sandstone, orange, the sandstone, green, the shade associated with the fan. And again, the regression triggered salt displacement salt in subsurface that again provoked the gross faults, and the gross fault initiate transgression and so on. And so we can see in seismic line the gross fault, and the group could map some zones based on seismic scale. Based on seismic scale, we can see a close view on based on well A, B, C, and D. We can see the third order sequence was subdivided into fourth order sequence using the seismic. So they moved from third order to fourth order, in which they recognize changing stratal stacking pattern at 10-meter scales, it means 40 to 80 meter thick sequences. By recognizing these zones that were producing water, they squeezed this interval and opened new interval that were saturated in oil. By doing so, production was stabilized. So the group knew they were in the good direction, but they had to move to even higher resolution, to fifth order resolution, in which the changing stratal stacking pattern is around meter scale, from 1.5 to 15 meter scale, or 15 meters thick, the sequence. So I have to zoom in this fourth order zone to see the framework of fifth order high resolution zones. Here we have this one, the subaerial conformant in top and bottom, the fourth order sequence. And you can see the gamma ray log, the lithology, yellow is sandstone, blue, carbonate, and green, shales, and the resistivity log. And we cannot recognize any stacking pattern by looking at the gamma ray log. But when looking at porosity log, depth, and neutronic log, we can see porosity became better at the middle of the sandstone. And then from this part, porosity is progressively deteriorated and going to ferrocement carbonates. So the group recognized maximum regressive surface were connected with the presence of the best reservoir that were subdivided by subarray conformity in fifth order. Then when they correlated, did well with the next one, it's around 140 meters apart. They identified 4 zones, A, B, C, D. And zone C, indeed well, showed it was completely water saturated. So how can you have a water zone on top of an oil zone? It might be different. And then by recognizing this, in these and other wells, they decided to squeeze this interval, squeeze the water saturated interval, and open oil interval that have never been opened before. By doing so, based on this fifth order reservoir zonation, the expected production declining like that were this one. In 10 years, the field experimented an increase in production that we say the field was rejuvenated and product 1.7 million barrels additionally. That equals roughly 1/4 of the accumulated production up to 2006. This volume also is responsible for a significant increase in 5.1% of oil recovery factor. And if you make a simple calculation, consider $50 a barrel, this surplus 1.7 million barrels equals $85 million during the period, roughly $9 million a year. Not too bad for a small oil field, right? Well, based on this experience, what we have learned so far? Well, we know that high resolution 6 strategic main objective, main application in the oil industry is to determine reservoir zonation and promote a better characterization of our reservoirs. Why? Because high resolution 6 stratigraphy highlights the reservoir's spatial and temporal distribution, as well as lateral connectivity. And we can map the heterogeneities, I mean the zone boundaries within the wells, within the oil field. So based on this framework, we can also properly distribute phases and petrophysical properties in our models. And when adjusting geologic and fluid flow models, we may achieve a better forecast for our product, for our project. And we have learned that diagnostic features are significant clues for improving our stratigraphic refinement in direction to a high resolution 6 stratigraphy. So high resolution 6 stratigraphy helped in major fields because it identifies water saturated washed zones and oil zones that have never been drained. By squeezing these water saturated zones and opening these new oil zones, it helps increase the production and trigger field rejuvenation. So the impact is incredible. Well, if you are interested in this topic, I think our corporation, the Reservoir Solution, we can offer deliver webinar training course and on 6 stratigraphy, especially associated with this impact on production performance. We also have a field course in Brazil and Portugal, or in course or in class or whatever, and we can customize the needs of our clients and search for the best solution they need. So I invite you, if you're interested in this topic, to surf on our website, Bagal Geo Consulting. Well, I'd like to finish this presentation by paraphrasing Professor William Richard Dixon, who said, "Rocks stay the same. What changes is the way we interpret them." And then I humbly add, interpretation can make a big difference for our business. So I'd like to thank you very much. Stay in touch with me if you need some information. And should you have any question, I'll be more than glad to answer it. Thank you very much.
Thank you, Mr. McGab, for this interesting presentation. I think that most of the attendees have new knowledge that will add to their experience and their career, inshallah. So I would like to thank you again for this effort and your time for this session.
You're welcome, my friend. Thank you very much.
Thank you. So for the attendees, if anyone have any question, please drop it into the Zoom chat, and the instructor will be more than happy to answer these questions. Actually, Mr. Magal, we have some questions into the Zoom chat. We have a question. How thick should be of the positional body, which will be easily detectable on seismic sections?
Thank you for your question, Mr. Kosom Javed. I'm sorry if I didn't pronounce your name correctly.
Okay.
Look, the seismic resolution depends a lot of things, right? So, depending on your seismic, depending if the shallow or deeper in subsurface, it depends on the parameters you acquired the survey, the seismic survey. But I would say that less than 20 meters is quite difficult to see in an average, right? On seismic line. So I have to go to subseismic scale and use well logs to perform a solid correlation.
Okay. We have another question. He is asking about the impact of well log vertical resolution.
I'm sorry, I didn't understand how many got the ultimate recovery.
No.
Well, depletion is a property. When you start production, we know the reservoir will be depleted. No way to do that without depletion. So I have to use another mechanism to recover the pressure of the reservoir. But these data can be useful to understand the reservoir behavior, the thickness of the electrical connectivity, whatever. And then the ultimate recovery, I say, when you finish, when you go to the highest resolution you have, and have done all effort to produce every single zone, when you go to EOR or IOR project, we can see, okay, how much oil could be recovered. And then we can see each steps and may add some portion of the oil recovery factor.
Okay, great. Another question, he is asking about the impact of well log vertical resolution.
That's a good question, Mr. Jeffrey. Well, the well log resolution is the best one to have. We have core, and from core we go to wells. The well resolution mostly show us phase association instead of single phases that compose our reservoir. So I think the well logs are very good to highlight the difference in phase association. If you use well logs with the sequence stratigraphic approach, the principles, and recognize in chord logs the stacking pattern and calibrate the well logs with this stacking pattern using whatever well log you have, you saw that gamma ray were not able to recognize the stacking pattern in this example I gave you today. But the people had the porosity logs. So you must find the best log to reproduce the stacking pattern. Once you get this, you can correlate the stacking pattern through the well logs and establish, identify the sequence stratigraphic surface that bound those zones. When you do that, you have a chronostratigraphic framework. And so you can change the way we correlate and you change the way you produce oil from your reservoir.
Okay. We have another question from Mr. Sunai. He is asking about what if the water gets into the new perf zone after squeezing the old perf ellipses?
Excellent question, Sidney. Excellent. It means that we are not yet with the final model. I'll say, if water come to the new open zone, we expect to have oil. It means that we are not controlling this reservoir distribution. We must strive a little bit more to get the better to get correlation. In this data, water come to the wells, just open interval, show that our correlation is not good. We might revise our correlation based on this data. That's why I told you, production data are very, very important that give us some clues that geological data alone do not give us.
Okay. Actually, we have many attendees that congratulating Mr. Magal for this interesting presentation. Thank you. Okay, we have a question from Mr. Pedro. He asking about how may I use depletion management of brown field with a high water saturation?
Yeah, Mr. Pedro, thank you for your question. Yeah, it's very common in major oil field, the brown fields. We produce a lot of water, and part of the production, we have some oil as well. So in this case, we must be even careful, because we must be able to determine where the water is coming from. And maybe we can try to achieve a further higher resolution that we have. And then we can, if it's possible, to separate oil from water. If we have different oil-water contact in this zone, that may be the case, and it is the case in most major oil fields. We must be aware of this and propose oil wells intervention that promote oil production and try to avoid the maximum the production of water. Be careful of recycling injection water. I mean, we inject water in one well and produce the same water in another well. Be careful of this because a loss of money, expensive energy, and this recycling do not improve production. So if you have this case, and if you have different zones with different oil-water contact, we must be very, very careful where we open the interval for production and control the pressure drawdown to avoid water production.
Okay, thank you. We have another question. He is asking about the high resolution sequence stratigraphy. What are seismic attributes that can be progressively improve the high resolution sequence stratigraphy interpretation? Which attribute can be used?
Well, it depends on the data, depends on the geology you have. But I wouldn't specify one attribute and say that's good and the other one not good. But for instance, RMS amplitude maps is very good to show the spatial distribution of the depositional system. Maybe it can be useful for determining the areal distribution of some actual elements. So it depends on the data you have, depends on the depositional system we are dealing with. But I would say try to use the attributes, but try to go further the resolution, the seismic resolution, because seismic resolution is not capable to capture the high resolution sequence we need to understand reservoir production and to improve production and decrease water production.
Okay, thank you. Actually, we are receiving many questions, but just for the time of the session, we can take another 2 questions. If your time, Mr. Magal, is suitable for that.
I'm sorry. Can you repeat, please?
Actually, we are receiving many questions, so so we can.
No worry. I have time. If you would like to go, no problem.
Okay, thank you. Thank you for your time. Okay, we have a question from Mr. Sydney. He is saying that despite the fact that the reservoir is heterogeneous, but after PHP or bottom hole pressure study, it was observed that the permeability is almost uniform vertically. Does that mean water cannot go to new shallow perforation depth of previous deep depth was squeezed?
Well, each oil field has its own characteristics. If you have a reservoir with such a vertical, almost uniform permeability, it means this zone alone can be mapped because the performance of permeability does not allow you to separate into higher zones. So you have to treat this as a single zone. And then compare it with the other zones you have in your oil field. I wouldn't guess any behavior because the permeability may change. I told you, may change if you have different architectural elements of phase association through the system tract. So the permeability behavior in one phase association may not be the same, for instance, in proximal to intermediate deposits. So be careful of that. Try to map the zigzag lines to see if we have the same behavior in different deposits. If the permeability in this case communicate very consistently, almost uniformly vertically, if the same behavior you observe in the next architectural element. If not, you can subdivide your reservoir zone into 2 or 3, depends on the performance of the permeability. And in this specific architectural element, we can try some strategies to improve production. But I wouldn't say you cannot use this one to avoid perforating shallow or deeper wards. I wouldn't say that. I wouldn't use this approach.
Mm-hmm. Okay. We have another question. At what point into a field life would you suggest it would be worthwhile to build the high-resolution geologic models? It is a question from Mr. Sam. Right from the beginning?
I wouldn't say high-resolution geologic models are regional because, you see, the higher resolution means higher frequency. And the mappability of surface, sequence stratigraphic surface that bound this sequence, high frequency, high resolution, means low hierarchy. So it's much more confined than regional, low frequency, high hierarchy sequences. So I would say that high resolution refinement, the high resolution framework are useful for places within the whole tract, the whole depositional system. I would never run a geological model, the regional geological model based on high resolution. If you like to have a regional model, you have to work with low resolution, high hierarchy, second or third order seismic scale sequences, okay?
Okay. We have another question. He is asking about which better is to do the correlation with chronostratigraphic or with lithostratigraphic?
Hello, Mr. John. Thank you for your question. I demonstrate you the danger it is if you use the lithostratigraphic approach. It has been so common because we are conditioned from the university, from our first years, graduation time, to correlate what seems equal. But when we do that, we cannot see the evolution of the system through time. So I strongly recommend you to abandon the lithostratigraphic approach and start immediately studying, and applying the chronostratigraphic approach. The case study I showed you today demonstrate the power of this chronostratigraphic correlation and the impact it has to rejuvenate oil fields that otherwise would be abandoned. And we can improve the production, rejuvenate oil fields just by admitting a new possibility of correlation. It means be updated in sedimentological and sequence-stratigraphy principles and start using immediately the chronostratigraphic approach.
Okay. We have another question. In order to achieve the water breakthrough as delineated from the study, was this achieved using the 4D seismic studies?
No, Mr. Oludegon, thank you for your question. When you get the first order, the group get the first order framework based on science, some interval that was water saturated interval was identified on top of these zones, and they were squeezed. They're closed for production. And the other were never open. They identified it was oil saturated. They opened to production. Only by doing that, the production was stabilized. But the seismic 4D, the 4D seismic I showed you was in an oil field in Brazil where we saw the movement of water within permeable zones. And they indicated the need for refinement, stratigraphic refinement in previously one single zone was subdivided in 3, 4, or 5 different zones. So the movement of water, the breakthrough of water, helped the group to understand the heterogeneity they had in the oil field and encouraged them to search for the higher resolution, not using seismic anymore, but only based on core and logs.
Okay. Let's see if we have another questions. Okay. Okay, so I think that we have no more questions. So thank you, Mr. Magal, for this interesting presentation and for asking many questions after the sessions. Actually, it was one of the most interesting sessions that we delivered as Reservoir Solutions. So thank you all for your time and effort exerting this interesting session.
Thank you very much. It's a my pleasure to collaborate with you. And if anyone has any other question, please just send me an email. I'll be more than glad to answer, okay? So, Mr. Abdullah, I hope we can continue this cooperation and we'll wait for next opportunities. Thank you very much.
For sure.
Thank everybody.
Sure. Thank you. Thank you. Thank you.
Thank you for this splendid audience. Thank you very much.
Thank you. Thank you. Thank you. Also, I would like to thank all the attendees for this time attending this session. And I would like to remind them if you wanted to get a certificate for attendance for these sessions, you can fill into the form that was sent into the Zoom chat. Also, if you would like to enroll into our upcoming events, you can enroll them by enrolling or registration into the form that will be sent also into the Zoom chat. So thank you all and hope you good night.